Hi folks, and welcome back to Physics with Captain Rod, making this one to help you out with number 26 in your homework. So we have, gotta get my pen on, okay. So we have this system, which is released from rest, really common physics type of language. The higher mass is 12 kilograms, the lower is 5. Let's see, the pulley from the previous problem has been replaced with a pulley with a moment of inertia of 3 kilogram meters squared, right? So that's referring to this over here. Let's see, calculate the speed of the 12 kilogram mass when it hits the floor. All right, so this is a classic, work energy type of application here. I would call this position 1. Now, when we say position 1, though, we're talking about the entire system. So this object is starting here. This one is starting here. And there are no velocities in picture 1. So there's no velocity vectors to worry about. Okay, now you draw picture 2. So the bigger mass is now down towards the floor. It has a velocity downward. The small mass is now up here somewhere. It has a velocity upward, which, looking at the picture, those two velocities should be the same. Right? And the pulley is rotating, so you should put a velocity for that, an omega 2. Okay. Now, write out the work energy theorem. You should have a PE1 term for this object, but not for the other. That's putting a datum at the floor. The pulley has a potential energy, but it is not changing in the problem, so you don't need to worry about it. And then the 5 kilogram mass is at the floor. So the PE1 term should only have one term. Okay? KE1 is 0 because it starts from rest. The work term is 0 again. There are no external forces acting on the system to change the total energy of the system. In fact, let me talk about the only external force acting on the system is at the pin. The pin applies some sort of external force up here. But the pin is not moving, so there's no work done by that force. Right? So there's no work terms at all to worry about. Again, as long as we define our system as the whole kit and caboodle. Okay? The PE2 term, okay, you should have something due to this guy. The KE2 is going to have 3 terms. One for this, one for this, and one for the pulley. Now, these two velocities are the same. They're the same, at least in magnitude. So when you get your work energy theorem written out and you look at that equation, you should have an unknown V and an unknown angular V. And I try to not skip over this. I try to describe this as best I can every time, all right? The V and the angular V are linked by the circular motion that's happening here at the pulley, all right? So if we imagine this point in red moving over to here, okay? This distance is the arc length, S. And it's equal to the radius of the pulley times whatever this change in angle is. I'll call it a change in theta. If you don't mind, I'm going to call this a delta S, a change in S. Right? This equation is coming from the definition of a radian. And if you divide it by time, the delta S over delta T becomes a V. And if you divide the right-hand side by time, the change in theta over change in time is what this is, the angular velocity. So you can use this to eliminate this in your work energy theorem. And that should get you where you need to go. So hopefully that'll be enough to get this problem done. I hope you enjoyed the video. Have a great day.